Welcome to Dormant Knowledge. I'm your host, Deb, and this is the podcast where you'll learn something fascinating while gently drifting off to sleep. Our goal is simple: to share interesting stories and ideas in a way that's engaging enough to capture your attention, but delivered at a pace that helps your mind relax and unwind. Whether you make it to the end or drift away somewhere in the middle, you'll hopefully absorb some knowledge along the way. We would love your support and feedback to keep this project going. You can find us at dormantknowledge.com or follow us on social media at Dormant Knowledge on Instagram and Facebook, or at dormant_knowledge, that's DRMNT_knowledge on X. We would also appreciate a donation to help defer production costs. You can find us on buymeacoffee.com at Dormant Knowledge Podcast. Any little bit helps. Tonight, we're exploring the strangest scientific revolution in human history: quantum mechanics. This year, 2025, marks the International Year of Quantum Science and Technology, celebrating 100 years since the birth of this bizarre and beautiful theory. So settle in, get comfortable, and let's begin our journey into the quantum world, a realm where particles exist in multiple places at once, where the very act of observation changes reality, and where the impossible happens every day. You know, it's funny right now as you're listening to this, quantum mechanics is working all around you. The LED lights in your room, the GPS that guided you home today, even the smartphone or computer playing this podcast, they all depend on quantum effects discovered by brilliant minds who, a century ago, thought they were going slightly mad. Because quantum mechanics, well, it doesn't make sense, not in the way we usually think about the world. But that's exactly what makes it so fascinating, and why it took some of the greatest minds in history decades to accept what the mathematics was telling them. Let me take you back to 1900. Max Planck was a respectable German physicist living in Berlin, conservative, methodical, not at all the type to start revolutions. He was working on what seemed like a simple problem. Why do hot objects glow the way they do? You've seen this, of course. Heat up a piece of metal and it glows red, then orange, then white hot. Scientists called this the black body radiation, the light emitted by a perfect absorber and emitter of heat. And there was a big problem. According to classical physics, a hot object should emit infinite energy. I know that sounds absurd, but here's why. Classical theory said that electromagnetic radiation, light, in other words, could have any energy value whatsoever, any frequency, any wavelength, any energy. And when you add up all those possible energies that a hot object could emit, you get infinity. They call it the ultraviolet catastrophe. And it was keeping physicists awake at night, not because it was dangerous, but because it meant their beautiful, elegant theories were fundamentally wrong. Planck was desperate. He tried everything to solve this problem using classical physics. Nothing worked. So in what he later called an act of desperation, he made a wild assumption. What if energy didn't come in any amount you wanted? What if it came in discrete packets, like coins in your pocket? He proposed that energy was quantized, meaning it came in indivisible chunks. The energy of light, he said, equals h times nu. E equals h times nu, where nu, that's the Greek letter that looks like a V, represents frequency, and h, H became known as Planck's constant. Planck's constant is an incredibly tiny number, about 6.626 times 10 to the negative 34th power. To give you a sense of how small that is, if you wrote it out in decimal form, you'd have a decimal point followed by 33 zeros before you got to the first significant digit. It's written as a lowercase h, and it became one of the most important numbers in physics. The formula is deceptively simple. E equals h times nu. Energy equals Planck's constant times frequency. But this simple equation changed everything. It said that light, electromagnetic radiation, doesn't come in any amount you want. It comes in specific quantized packets that Planck called quanta. And you know what? It worked. The formula perfectly explained black body radiation. No more infinite energies, no more ultraviolet catastrophe. But Planck himself was deeply uncomfortable with what he'd done. He spent years trying to explain away the quantum hypothesis, trying to make it fit with classical physics. He couldn't know it then, but he'd just opened the door to the strangest century in the history of science. 5 years later, in 1905, a young patent clerk named Albert Einstein was having his miracle year. We often think of 1905 as the year of relativity, but Einstein actually published another paper that year, one that would later win him the Nobel Prize. He was thinking about something called the photoelectric effect. Here's the puzzle. When you shine light on certain metals, electrons get knocked out. That part makes sense, but here's what didn't make sense. The energy of those electrons depends only on the color of the light, not how bright it is. So if you shine dim blue light on zinc, you get high energy electrons. But if you shine incredibly bright red light on the same zinc, nothing. No electrons at all. Classical physics said this was impossible. After all, bright light has more energy than dim light, right? So bright red light should definitely knock out more electrons than dim blue light. Einstein realized that Planck's quantum idea was the key. What if light itself comes in discrete packets, particles of light that he called photons? Each photon carries a specific amount of energy. E equals h times f, where f is frequency. So blue light photons, higher frequency, carry more energy than red light photons. Now the photoelectric effect made perfect sense. Each electron gets knocked out by a single photon. Blue photons have enough energy to free electrons from zinc. Red photons, no matter how many of them there are, simply don't have enough individual energy to do the job. It's like trying to break down a door. Having 1,000 people gently push on it won't work, but one person with a sledgehammer might. This was revolutionary because it meant light behaves like both a wave and a particle. Waves for things like interference and diffraction, particles for things like the photoelectric effect. Einstein had taken Planck's desperate hypothesis and showed that it revealed something fundamental about the nature of light itself. But even Einstein would later struggle with where this quantum thinking was leading physics. Around the same time, a young Danish physicist named Niels Bohr was wrestling with another impossible problem, the atom itself. Ernest Rutherford had recently discovered that atoms have a tiny, dense nucleus surrounded by electrons. The obvious model was planetary, electrons orbiting the nucleus like planets around the sun. But there was a fatal flaw. According to classical electromagnetic theory, an orbiting electron should constantly radiate away energy and spiral into the nucleus in a tiny fraction of a second. Every atom should collapse instantly, but obviously that doesn't happen. You and I and everything around us are made of stable atoms. Bohr had what we might call an audacious thought. What if electrons, like light, were subject to quantum rules? What if electrons could only exist in specific, allowed orbits, quantized energy levels? He proposed that electrons orbit the nucleus only at certain discrete distances, like runners who can only run on specific tracks, never between them. The mathematics worked out beautifully for hydrogen, the simplest atom. The energy of an electron in the nth orbit, where n is just a whole number like 1, 2, 3, equals negative 13.6 electron volts divided by n squared. E equals negative 13.6 eV over n squared. An electron volt, or eV, is just a convenient unit of energy, the energy an electron gains when accelerated through 1 volt of electrical potential. So the electron in hydrogen's lowest orbit has an energy of negative 13.6 eV. In the second orbit, it's negative 3.4 eV. In the third, negative 1.5 eV, and so on. But here's where it gets really strange. Bohr said that when an electron moves from one orbit to another, it doesn't gradually spiral down like a classical object would. Instead, it makes an instantaneous quantum jump, disappearing from one orbit and reappearing in another, emitting or absorbing a photon in the process. This explains something that had puzzled scientists for decades: why different elements produce different colors of light when heated. Each element has its own unique set of spectral lines, specific colors it emits or absorbs. These lines are like fingerprints, and now Bohr could explain why. Each line corresponds to an electron jumping between specific energy levels. The mathematics were elegant. The predictions were accurate, but the implications were unsettling. Electrons apparently could teleport. They could exist at one energy level, then instantaneously exist at another, without ever being in between. Even Bohr admitted it was strange, but the evidence was overwhelming. The quantum world, it seemed, operated by rules that defied everyday experience. I'm going to take a quick break here. When we come back, we'll explore how a French aristocrat's seemingly crazy idea opened the door to even stranger quantum revelations. Welcome back to Dormant Knowledge. In 1924, a French prince, yes, an actual prince, submitted one of the most revolutionary PhD theses in the history of science. Louis de Broglie came from one of France's oldest noble families. He'd served in the wireless service during World War I, working with radio waves, and that experience had given him a peculiar idea. Einstein had shown that light, which everyone knew was a wave, could also behave like a particle. De Broglie wondered, if waves can behave like particles, why can't particles behave like waves? It seemed absurd. A baseball behaving like a wave, an electron creating interference patterns like ripples on a pond. But de Broglie worked out the mathematics. If particles have wave-like properties, he reasoned, their wavelength should equal Planck's constant divided by their momentum. Lambda equals h over p. Lambda equals h over p, where lambda, that's the Greek letter that looks like an upside-down Y, represents wavelength, and p represents momentum. Now, before you start worrying about whether you might suddenly start diffracting around doorways, let's calculate your own quantum wavelength. Say you're a 70-kilogram person walking at 1 meter per second. Your momentum is 70 kilogram meters per second. Planck's constant is about 6.6 times 10 to the negative 34th. So your wavelength would be, well, unimaginably small, about 10 to the negative 35th meters. That's many, many times smaller than an atomic nucleus. So, no, you won't be creating interference patterns anytime soon. But electrons are light enough that their wavelengths are comparable to the spacing between atoms and crystals. And sure enough, when physicists fired electrons at crystal surfaces, they got diffraction patterns, the distinctive interference patterns that only waves can create. Matter waves. It was perhaps the most philosophically disturbing idea yet. If an electron is both a particle and a wave, what is it really? The answer, it turned out, would depend on how you looked at it. Sometimes it behaves like a particle, sometimes like a wave, but never both at the same time. De Broglie's insight opened the door to modern quantum mechanics. It suggested that at the quantum level, the distinction between waves and particles, a distinction that seems so fundamental to our understanding of reality, simply breaks down. Reality, it seemed, was far stranger than anyone had imagined. By 1925, physics was in crisis. The old quantum theory, Planck's quanta, Einstein's photons, Bohr's energy levels, explained a lot, but it was clearly incomplete. Something more fundamental was needed. That something came from an unlikely source, a 23-year-old German physicist named Werner Heisenberg, who was suffering from hay fever. In June 1925, Heisenberg escaped to Heligoland, a tiny pollen-free island in the North Sea. There, in a burst of inspiration that lasted just a few days, he invented an entirely new kind of physics. He called it matrix mechanics. Now, matrices, those rectangular arrays of numbers that give math students nightmares, were barely known to most physicists at the time. Even Heisenberg didn't really understand them initially. But he realized that to describe quantum systems properly, you couldn't use ordinary numbers. You needed mathematical objects that didn't commute, where A times B doesn't equal B times A. This led to the most famous principle in quantum mechanics, the uncertainty principle. Heisenberg showed that certain pairs of properties, like position and momentum, can't be measured precisely at the same time. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. Mathematically, it's written as delta x times delta p is greater than or equal to h bar over 2. Delta means uncertainty in or change in, and is represented by the lowercase Greek letter that looks kind of like a cursive D. H bar is Planck's constant divided by 2 pi. It's written as an H with a line through it. But here's the crucial point. This isn't just about our measuring instruments being clumsy. It's not that we're disturbing the particle when we measure it, though that happens too. It's that the particle doesn't have precise values for both position and momentum simultaneously. At the quantum level, nature itself is fundamentally uncertain. Around the same time, an Austrian physicist named Erwin Schrödinger was developing his own approach. Schrödinger was, well, let's say he was a colorful character. He had unconventional personal relationships and a passion for ancient philosophy. But he also had brilliant mathematical intuition. Schrödinger developed wave mechanics, a way of describing quantum systems using wave functions. His famous equation looks intimidating. I times h bar times the partial derivative of psi with respect to time equals h hat times psi. Let me break that down for you. The I is the imaginary number, the square root of -1. Psi, the Greek letter that looks like a little pitchfork, represents the wave function. H hat, written as an H with a little hat on top, is called the Hamiltonian operator. Think of it as a mathematical recipe that tells you about the energy of the system. You don't need to understand the mathematics to appreciate what this equation does. It tells us how quantum wave functions evolve over time. Think of it as the quantum equivalent of Newton's laws of motion, but instead of predicting exactly where a particle will be, it predicts the probability of finding it anywhere. The wave function, psi, doesn't describe a physical wave rippling through space. It describes probability amplitudes. When you square the wave function, you get the probability of finding a particle at a particular location. The wave function itself can involve complex numbers involving that mysterious quantity I, the square root of -1, but the probabilities it predicts are always real and positive. And here's perhaps the strangest part. Before you measure a quantum particle, it exists in what's called a superposition, a combination of all possible states simultaneously. The particle isn't in any definite location until you observe it. The act of measurement forces it to choose a specific state. It turned out that Heisenberg's matrix mechanics and Schrödinger's wave mechanics were mathematically equivalent, two different ways of describing the same underlying quantum reality. But that reality was becoming increasingly strange. The Fifth Solvay Conference convened in Brussels in October 1927. It was a gathering of the greatest minds in physics: Einstein, Bohr, Heisenberg, Schrödinger, and many others. The topic was electrons and photons. But what really happened was the most famous philosophical debate in the history of science. By this time, the mathematics of quantum mechanics was largely complete, but what did it mean? Niels Bohr and his colleagues in Copenhagen had developed what became known as the Copenhagen interpretation. Their view was radical. Quantum mechanics is complete as it stands. There are no hidden variables, no deeper reality behind the wave function. The probabilistic nature of quantum mechanics reflects a fundamental feature of reality itself. Einstein couldn't accept this. God does not play dice with the universe, he famously declared. He believed that quantum mechanics, however successful, must be incomplete. There had to be some deeper, deterministic theory that would restore certainty to physics. Bohr's response, according to legend, was, "Einstein, stop telling God what to do." During the conference, Einstein would spend his days trying to construct thought experiments that would expose contradictions in quantum mechanics. Each morning, he'd present his latest puzzle to Bohr, and each evening, after careful consideration, Bohr would find the flaw in Einstein's reasoning. One of Einstein's most famous challenges involved what he called the EPR paradox, named after Einstein and his colleagues Podolsky and Rosen. The paradox involved quantum entanglement, though they didn't use that term. If two particles interact and then separate, quantum mechanics says they remain connected in a strange way. Measuring one particle instantly affects the other, no matter how far apart they are. Einstein called this the spukhafte Fernwirkung, spooky action at a distance. He argued that this proved quantum mechanics was incomplete. How could one particle instantly know what happened to its distant partner? But Bohr maintained that there was no contradiction. The entangled particles, he said, should be considered as a single, indivisible quantum system. They don't have independent realities until measured up. Schrödinger, meanwhile, was growing increasingly uncomfortable with the implications of the theory he'd helped create. In 1935, he devised a thought experiment that would become even more famous than the EPR paradox, Schrödinger's cat. Imagine, he said, a cat in a sealed box with a Geiger counter connected to a hammer that will break a flask of poison if the counter detects radiation from a radioactive atom. Quantum mechanics says that, until observed, the atom exists in a superposition of decayed and not decayed states. Therefore, the cat should also exist in a superposition of dead and alive states. Schrödinger wasn't trying to defend quantum mechanics with his thought experiment. He was trying to show how absurd it was. How could a cat be both dead and alive, yet the mathematics of quantum mechanics seemed to demand exactly that? Einstein spent the rest of his career, more than 20 years, trying to prove quantum mechanics incomplete. He died in 1955, convinced that God is subtle but not malicious, and that a deeper, more reasonable theory would eventually be found. He was, in this one case, wrong. I'm going to take another brief break here. When we return, we'll explore how later experiments proved that Einstein's intuition about the universe was incorrect, and how quantum entanglement really is as spooky as it sounds. Welcome back to Dormant Knowledge. For decades, the debate between Einstein and Bohr remained philosophical. Both interpretations of quantum mechanics made the same prediction, so there was no way to test which was correct. Then, in 1964, an Irish physicist named John Bell changed everything. Bell proved mathematically that any theory based on local realism, the idea that objects have definite properties and that nothing can influence something else instantaneously across a distance, must satisfy certain inequalities. But quantum mechanics predicts violations of these Bell inequalities. In other words, Bell showed that you could actually test whether the universe was the way Einstein thought it should be. If Einstein was right, certain correlations between measurements would have upper limits. If Bohr was right, those correlations could be stronger. The first decisive test came in the early 1980s when French physicist Alain Aspect performed a series of elegant experiments with entangled photons. The results were clear. Bell's inequalities were violated. Einstein's local realism was wrong. But what does this actually mean? Let's think about quantum entanglement more carefully. When two particles become entangled, they form a single quantum system. You can't describe one particle independently of the other, even when they're separated by vast distances. Imagine two particles with a property called spin. In quantum mechanics, a particle doesn't have a definite spin direction until you measure it. Before measurement, it exists in a superposition of spinning up and spinning down. Now, if two particles are entangled in a special way, their spins are correlated. If you measure one and find it spinning up, you'll instantly know that the other, no matter how far away, will be found spinning down when measured. This isn't because the particles agreed on their spins when they were created. They genuinely don't have definite spins until measured. The measurement of one particle somehow causes both particles to choose correlated spins instantaneously. Einstein thought this was impossible. Information, he believed, couldn't travel faster than light. And indeed, quantum entanglement doesn't allow you to send information faster than light. You can't use it to send messages, but it does mean that the universe is fundamentally non-local, meaning that distant objects can be connected in ways that defy our everyday intuition. Modern experiments have verified quantum entanglement over distances of hundreds of kilometers using satellites and fiber optic cables. The correlations are exactly as quantum mechanics predicts, no matter how far apart the particles are. We live in a world where particles can be instantaneously connected across the vastness of space. Einstein called it spooky, and it really is. But it's also real. You might think that quantum mechanics, with all its philosophical puzzles and mathematical abstractions, is purely academic. But you'd be wrong. Quantum mechanics has given us technologies that have transformed civilization. Take the laser, for instance. Laser stands for light amplification by a stimulated emission of radiation. The key word is stimulated. In normal emission, atoms spontaneously release photons at random times, but Einstein predicted another process, stimulated emission. When a photon of just the right energy hits the excited atom, it can stimulate the atom to emit another photon that's identical in every way. Same frequency, same phase, same direction. This is pure quantum mechanics. You create a population inversion, more atoms in excited states than in ground states. And then one photon can trigger an avalanche of identical photons. The result is coherent light, a laser beam. Lasers are everywhere now. They read the information on your CDs and DVDs. They perform delicate eye surgery. They cut metal in factories. They enable fiber optic communications. Every barcode scanner, every laser pointer, every optical communication system depends on stimulated emission, a purely quantum mechanical process. LEDs, light-emitting diodes, work by a related quantum process. When an electron in a semiconductor drops from a higher energy level to a lower one, it emits a photon. The color of the light depends on the energy gap between the levels, which depends on the quantum properties of the semiconductor material. Even your computer depends on quantum mechanics. Every transistor in your smartphone, and there are billions of them, relies on quantum tunneling. This is the eerie quantum effect where particles can pass through barriers that classical physics says should be impenetrable. Think of it this way. Classically, if you roll a ball toward a hill, the ball needs enough energy to go over the hill. But quantum mechanically, there's a small probability that the ball can tunnel through the hill and appear on the other side, even without enough energy to go over it. In a transistor, electrons tunnel through barriers of silicon dioxide, barriers that should be impenetrable according to classical physics. The quantum tunneling allows the precise control of electrical current that makes digital electronics possible. Your GPS system also depends on quantum mechanics in multiple ways. The atomic clocks in GPS satellites rely on precise quantum transitions in cesium atoms, and the system must account for both special and general relativistic effects. Einstein's theories that grew out of the same intellectual revolution that gave us quantum mechanics. MRI machines, magnetic resonance imaging, work by manipulating the quantum mechanical property called nuclear spin. Protons in your body have quantum spins that can be aligned and manipulated by magnetic fields. When the spins flip, they emit radio waves that can be detected and used to create detailed images of your internal structure. But these first-generation quantum technologies, remarkable as they are, may be just the beginning. We're now entering what some call the second quantum revolution. The quantum computers being developed today don't just use quantum effects in their components. They use quantum mechanical principles like superposition and entanglement as their fundamental operating principles. Where a classical computer bit can be either 0 or 1, a quantum bit, a qubit, can be in a superposition of both 0 and 1 simultaneously. This allows quantum computers to, in principle, perform certain calculations exponentially faster than classical computers, factoring large numbers, searching databases, simulating quantum systems. Tasks that would take classical computers longer than the age of the universe might be solvable by quantum computers in minutes. Quantum cryptography promises unbreakable codes based on the fundamental principles of quantum mechanics. If someone tries to eavesdrop on a quantum encrypted message, the act of observation necessarily disturbs the quantum states being used to encode the information, alerting the legitimate users to the presence of the eavesdropper. Quantum sensors are becoming incredibly precise tools for measuring everything from gravitational waves to magnetic fields. The LIGO detectors that first detected gravitational waves use quantum techniques to reduce noise and increase sensitivity. Some researchers even talk about a quantum internet, a network where quantum information could be transmitted between quantum computers using entangled particles as the communication medium. All of this springs from those strange ideas that emerged a century ago when a few brilliant minds tried to understand why hot objects glow the way they do. You might think that after 100 years we'd have quantum mechanics all figured out, but in many ways the mystery has only deepened. The measurement problem, for instance, remains unsolved. Quantum mechanics tells us that particles exist in superpositions until measured. But what exactly constitutes a measurement? When does the wave function collapse from a superposition of states to a definite state? Some physicists, following the Copenhagen interpretation, say this is simply how nature works. The wave function collapse is a fundamental feature of reality. Others, like Hugh Everett III, proposed the many worlds interpretation. The wave function never collapses. Instead, every quantum measurement splits the universe into multiple parallel realities, each corresponding to a different measurement outcome. In many worlds quantum mechanics, Schrödinger's cat is both dead and alive, but in different branches of reality. We only perceive one branch, the one we happen to inhabit, so we see either a dead cat or a live cat, never both. Other interpretations have been proposed. David Bohm spelled Bohm, developed a theory with hidden variables that reproduces all the predictions of quantum mechanics while maintaining determinism. The catch is that these hidden variables must be non-local. They must allow instantaneous influences across arbitrary distances. Some researchers explore ideas about quantum consciousness, the notion that consciousness itself might be a quantum mechanical phenomenon. Roger Penrose and Stuart Hameroff have proposed that quantum processes in structures called microtubules in brain cells might be responsible for consciousness. Most neuroscientists and physicists are skeptical of these ideas. The brain seems too warm and noisy for delicate quantum effects to persist long enough to influence cognition. But the relationship between the quantum world and the classical world of our everyday experience remains mysterious. There's also the fine-tuning problem, the fundamental constants of nature, Planck's constant, the speed of light, the strength of the electromagnetic force, seem to be precisely tuned to allow the existence of atoms, stars, planets, and life. Change any of these constants by even a small amount, and the universe would be a very different, probably lifeless place. Some physicists invoke the anthropic principle. We observe these particular values because we exist to observe them. In universes with different constants, there would be no observers. The many worlds interpretation suggests there might be countless universes with different physical laws, and we naturally find ourselves in one compatible with our existence. Quantum field theory, the extension of quantum mechanics to high energies and relativistic speeds, has its own mysteries. The Higgs field, dark matter, dark energy, all are quantum phenomena that we're still struggling to understand. And perhaps most mysteriously of all, there's the question that Einstein posed but never answered. Why does mathematics describe the physical world so precisely? The fact that human mathematics, abstract symbols and equations, can predict the behavior of quantum particles with extraordinary accuracy is, when you think about it, almost as strange as quantum mechanics itself. Eugene Wigner called it the unreasonable effectiveness of mathematics and the natural sciences. Why should our mental constructs correspond so precisely to physical reality? 100 years after Planck's quantum hypothesis, we have technologies that would seem like magic to our ancestors, but the fundamental questions about the nature of reality, consciousness, and the relationship between mathematics and physics remain as mysterious as ever. So here we are, a century after Max Planck reluctantly introduced the quantum hypothesis to solve a simple problem about glowing objects. What started as an act of desperation became the most successful theory in the history of science. Quantum mechanics has given us lasers and LEDs, computers and smartphones, MRI scanners, and GPS systems. It's revealed that reality is far stranger than our ancestors ever imagined, a place where particles tunnel through barriers, exist in multiple states simultaneously, and remain mysteriously connected across vast distances. But perhaps the most remarkable thing about quantum mechanics is how it challenges our most basic assumptions about the nature of reality. Before quantum mechanics, we thought the world consisted of definite objects with definite properties, evolving according to deterministic laws. Quantum mechanics revealed a universe that is fundamentally probabilistic, where the act of observation plays a crucial role in determining what becomes real. Einstein, who helped birth quantum theory but never fully accepted its implications, once said that the most incomprehensible thing about the universe is that it is comprehensible. He was referring to the mysterious fact that human beings, products of billions of years of evolution on a small planet, somehow developed minds capable of understanding the deepest laws of physics. Planck himself, reflecting on his career near its end, said that the quantum hypothesis represented one of the most fruitful intellectual enterprises ever undertaken by human beings. He was proud of what his desperate gamble had unleashed, even though he never fully understood where it would lead. Today, as we enter what some call the second quantum revolution, we're learning to harness quantum mechanics not just in our own technologies, but as a tool for computation and communication. Quantum computers, may soon solve problems that would take classical computers longer than the age of the universe. Quantum networks may allow us to communicate with perfect security across global distances. But even as we learn to manipulate quantum systems with increasing sophistication, the fundamental mysteries remain. What is the wave function, really? Why does measurement seem special? Is consciousness somehow quantum mechanical? Do parallel universes exist? These questions may keep physicists and philosophers busy for another century, and that's part of what makes quantum mechanics so beautiful. It's not just a collection of techniques for predicting experimental results. It's a profound meditation on the nature of reality itself. As you drift off to sleep tonight, remember that you live in a quantum world. The atoms in your body, the photons carrying moonlight to your eyes, the electrons flowing through the device playing this podcast, they all dance to quantum rules that would have seemed impossible to scientists just over a century ago. We've learned to predict the quantum dance, to harness it, to build technologies that depend on it, but we still don't fully understand why the universe chose to be quantum mechanical rather than classical, why reality is probabilistic rather than deterministic, why observation seems to play such a fundamental role in determining what becomes real. Perhaps that's as it should be. Science, at its best, doesn't just answer questions. It reveals new mysteries we never knew existed. Quantum mechanics has shown us that the universe is far more strange and wonderful than we ever dared imagine. And in doing so, it reminds us that human curiosity, the drive to understand our world, even when that understanding challenges our most basic assumptions, may be the most remarkable phenomenon of all. Thank you for listening to Dormant Knowledge. If you're still awake and hearing my voice, I appreciate your attention. But if you've drifted off to sleep somewhere along the way, which was partly the goal, then you won't hear me say this anyway. Either way, I hope some knowledge about the quantum century has made its way into your consciousness or perhaps your dreams. Until next time, this is Deb wishing you restful nights and curious days.